Okay, so in this video, we're going to go through the solutions to this homework where you have to graph the derivative. Just remember that the derivative represents the slope of the tangent line of the function at every point. I just want to try and get rid of this control rate here. Okay. All right, so if we look at this first, this is the graph of a function, and we want to graph its derivative. So remember, the derivative equals the slope of the tangent. So if I just picture every point along this graph, which is a line, what's the slope at every point? Well, the first thing is we should realize is that it's a line, and the slope of a line never changes. So its slope can be calculated pretty easy by creating a little slope triangle. So I'm going to try and find a lattice point here. And I think I've got 1 and 1 right here. So by my slope triangle, I'm going down 1 and to the right 2. We know that the slope of a line never changes. So the slope of this line is a constant value of negative 1/2. That represents the derivative at every point. So all I'm going to do now is change this to x versus f prime. And this is a constant function. And I graph a constant, a horizontal line through y equals negative 1/2. This represents that the slope at this point is negative 1/2. The slope at this point is negative 1/2. The slope at that point is negative 1/2, and etc. The slope at every point is negative 1/2 because the slope of a line never changes. In number 2, what do you want to look for? You want to first look for where the derivative equals 0. And that's going to happen where you have a horizontal tangent on the graph. I have a horizontal tangent right here where the slope would be 0. So that means at this x value, the graph of the derivative has to hit the x-axis. Now to graph the other slopes, I need to know two things. I need to know whether the slope is positive or negative, and whether it gets more positive, less positive, if it's negative, less negative, or more negative. And remember now, this is x versus f prime. So the first thing I'll do is picture a bunch of tangent lines along this graph. And I can clearly see that the slopes are all positive, but they're getting less positive. So when x is this number here, it's a pretty strong positive, but they're getting less positive until the values become 0, which is right here. So like when x is negative 4, maybe I get a positive 3. When x is negative 3, maybe I get a positive 2. Because remember, this is x versus f prime. So above the x-axis is where f primes are positive, and below the x-axis is where f primes are negative. And on the x-axis, that's where f primes are 0. And then now, as I roll over the top, again, what's the first thing? My slopes are negative, more negative or less negative. So to me, they're getting less negative. Oh, well, I'm sorry, more negative. So maybe like -1, -2. These tangent lines are getting steeper in a negative direction. So there is such a case of a good approximation of a graph of the derivative. Does it make sense? I think so, because this is some quadratic function of something of negative x squared. I can find the precise function. We don't really need to. And the derivative of that is a line of a negative slope. So something along that line would be a good approximation of the derivative. So number 3 gets a little more involved because we got some numerous places where we have a horizontal tangent. So again, that first step is look where you have a horizontal tangent. And that's going to divide up your derivative graph. And those are the x's where I have a horizontal tangent. Now work within each of those chunks. Again, what are my signs of my slope? They're negative, but they're getting less negative. So when x is this value here, like somewhere down here, we don't really care what they are, they're just getting less and less negative, and now the slope becomes 0. All right, let's roll over here, and now I get positive, but from about here onward, right about here on, my slopes are positive still, but they get less positive. So from -2 to this, my slopes are getting more positive. So I'm getting more and more above the axis. But then from about here to here, they get less positive. And then they become 0. Now I roll over the top up here, and I notice that my slopes get more and more negative. That's more and more negative. Now right about here, my slopes are still negative, but they get less negative, and then they hit 0, which is right here. And then from here on out, the slopes get more and more positive. This is an important point. That's called the point of inflection on the graph of f. It's where the function changes from concave down to concave up. Let's go down to number 5, a little more clearly drawn. So where do we have horizontal tangents? Here and here. That means my derivative is going to be 0 at those points. It's just an approximation, like maybe that's like 2 1/4. Again, are the slopes positive? Yes, here, but they're getting less positive. So just somewhere when x is this value, there's a positive slope, and they're getting less and less positive. Now, the slopes get more negative, I would say. But then somewhere, they start to get less negative. So they're negative, but they get less negative, and then they become 0, which is here. So I'm getting something, like this right through here, And then, like I said, like right about here maybe is where they start to get less and less negative, then they become 0. And what are my slopes here? All positive. So does this graph somewhat make sense? And I would say absolutely, because I may have a third-degree polynomial right here, and the derivative of a third-degree polynomial is some x² function. So I do have kind of like a shape of a parabola through here, probably. You know what I mean? Right through there. Just want to see what the rest of this is. Okay. And then over here, these are a little more homemade, I think, so sometimes they're a little hard to decide, like where that's horizontal tangent. But I see a flat toe up there, and I really do see something down here that's horizontal. So they don't always appear extremely flat, remember? So there I have those breaking points in my derivative. So then now, what am I going to do? Draw my tangent lines. And what are they? Positive, but getting less positive. So where is a positive f prime? It's above. Positive values, getting less positive and becomes 0. Now I roll over the top, and they become more and more negative. But then I would say now they start to get less negative to become 0. And then here I would strictly say that all the slopes, again, are all negative, but now they start to get more and more negative. So this function seems to look like this, the derivative, because this function's always decreasing. And when the function is decreasing, its derivative is always going to be less than 0, because all the slopes are negative. All these slopes are negative. But what happens is they start to get more and more negative till about here. So it's going down. Then they get less negative and become 0. Then they resume becoming more and more and more negative. And that's a good approximation to that graph. And you can do some matching here in this one. So you have to match these. Again, think about these. This is the function, and this is its derivative over here. Think about this. If this is a right here, this is a parabola, so its derivative is going to have to be a linear function. Or the function was x cubed. Sorry, I mean the function's x cubed. If the function was x squared, it's a linear function. So again, where do I have a horizontal tangent? There is at the origin. And here I have a bunch of what positive, negative slopes, but they're getting more and more negative. And oh wait, I'm going backwards here. Hold on, that's y prime. This is my function. Sorry, so it's still the same thing, but it's over here. So this is my function. There's my horizontal tangent. Is at the origin. These are all negative, but getting more negative. So to me, that would be such a graph. Then it becomes 0, positive and positive slopes, so more and more positive. Here in number 2, I have a horizontal tangent here. My slopes are always all positive, but they get less positive, which would be here. And then they get resuming back to getting more and more positive. So to me, this would be A, and this seems to be B so far. And then this is looks like a cosine graph to me, and its derivative is going to be negative sine. I could see that already. So here I have 3 horizontal tangents. So it's a 0, 0, and a 0. And I could visually see that I have a 0 slope there, kind of. But these here are all negative, and they are getting more and more negative. So somewhere about here. Then about here, they start to get less negative and become 0, which is right here. Then it becomes more and more positive slopes. And then I'd say somewhere about right about here, I guess, they start to get less and less positive, and then they become 0. And then it becomes more and more negative. And then I would say, about here, it starts to become less and less negative. So it becomes 0, and then so forth. In this one, I could see that I have 3 horizontal tangents. So I got 3 zeros on F prime. I have these to be what sign? They are negative and getting less negative. So I could see that happening. Then it's 0. Then they get more positive, but then they get less positive. So more and more positive, then less positive, and now 0. Then they're going to get negative again, but then less negative, then 0, and then forever positive. Again, like what you have to look for is on the graph of a function, if I can do a decent job here of this. Yeah, like right here. So like this is where my derivative is 0. This is where it's 0. All my slopes are negative. But right here, where the graph changes from concave down to concave up, that's where my slopes will start to change from increasing to decreasing or vice versa. So here my slopes are getting more and more negative, but at that point of inflection, the slopes are negative, but they're getting less negative. So how would I graph that? Well, right here is where my derivative has to hit the x-axis at that point, because that's where I have a horizontal tangent. So then now from this point to that x value, they get more and more negative. But then now from this x to this x, they get less negative and then become 0. And just to reinforce some derivative rules here at the end, if I can get this here, in this part derivative challenge number 2, just to talk through these pretty quickly, I hope that we would use algebra first and rewrite that as that. And then I would just use a power rule from there, dropping down the power, repeating the x, and decreasing it by 1. In this one here, I would do a quotient rule. So it's the bottom times root of the top minus the top times root of the bottom, all over the bottom squared. And I think that's pretty easy to clean up there. And number 3, f prime of t, the root of sine is cosine. It's a function within a function. Repeat the inside and times it by the derivative of the inside, which is pi over 3. But I need to replace t with 2. And the cosine of 2/3 pi, 2/3 pi puts me here. Pi over 3 is my reference angle. Across from that's root 3, -1 and 2. Cosine is the x over the r, so it's -1/2 times pi over 3, which is negative pi over 6. And number 4, I would do a quotient rule. So it's the bottom times root of the top minus the top times root of the bottom, all over the bottom squared, which would be to the 4th power. And this cleaned up would become that over x to the 4th. And number 5, the derivative would be found by dropping down the power, repeating the inside, decreasing the power by 1, and timesing it by the derivative of the inside. In 6, it would be a product rule. It would be the first times the derivative of the second, which is e to the 3t times 3, plus the second times the derivative of the first. In number 7, I'm just going to take this to the outside. So f prime of x equals 4, parentheses, sine of e to the 2x to the 3rd. So I drop down the power, repeat the inside, decrease the power by 1, and then times it by the derivative of the inside. And the derivative of sine is cosine. Repeat the inside, and then times it by the derivative of the inside again. And number 8, it's just going to be an easy product rule. It's the first times the derivative of the second plus the second times the derivative of the first. And 2 very important ones on implicit is I'm actually going to rewrite this as ln of x plus ln of y equals y. The derivative of ln of x is 1 over x, but the derivative of ln of y is 1 over the inside times the derivative of the inside, which is 1 dy dx. And the derivative of y is dy dx. So what we're going to do is get the dy dx's to one side, and then subtracting over the -1 over x. Factor out a dy dx, and what's left is this. Okay? Then I'm going to divide by that. So then dy dx equals -1 over x divided by 1 over y minus 1. And then how would you simplify that is you'd make a common denominator by multiplying this by y over y, and you'd have -1 over x from the top. Stay with it. And then just invert and multiply this to become y over 1 minus y. And there would be your answer cleaned up. And here, last but not least, to finish it out, this is a product rule, so it's x squared times dy dx plus y times 2x plus 2 equals 0. And then just easily, guys, dy dx equals, subtract over the 2, subtract over the 2xy, and then just divide by that measly x squared there. And then just sub in 3 and 1. So when x is 3 and y is 1, there's my slope, -2, right? Minus 6 over 9, I'm getting is -8/9. It's really important to keep reviewing your derivative rules here. Okay, I hope that helps.